Good morning, friends. Myself, Shobit M. Chanbok from Reva Invest, Bangalore. But today's topic is dopant role on negative differential resistance in poly-3-methylthiophene devices. Abstract. Poly-3-methylthiophene polymer is electrochemically synthesized on stainless steel substrate and a sandwich device structure is realized by placing top metal contact to fabricate two-terminal device. The current voltage measurements are carried out to probe the negative differential resistance and charge transport in P3MT devices. The polymer is first doped with PF6, that is hexafluorophosphate and perchloride dopants, and then dedoped for 30 seconds. The magnitude of NDR peak to valley current ratio depends on the voltage swept and the type of dopants. We propose that the reason for NDR anomaly is dopant induced trap states. Keywords are negative differential resistance, electropolymerization, and current voltage. Introduction. Conjugated conducting polymer P3MT is grown on stainless steel substrate using electropolymerization method. The conjugated polymer mainly consists of pi conjugated chains. The pi conjugated chains have alternative single and double bonds along the backbone of the polymer chain, so that the pi bonded orbitals of carbon atoms overlap. This leads to the delocalization of electron cloud along the pi conjugation of the backbone of polymer chain. This delocalization of electron is mainly responsible for the electrical conduction in polymers. Conjugated polymers are used in many devices like diodes, LEDs, solar cell, FETs, sensors, memory devices, etc. Synthesis method. We synthesized P3MT using electrochemical polymerization. As mentioned earlier, we add 3-methylthiophene, the monomer and the dopant into an organic solvent, and we dip we have a customized cell, and we dip the electrodes to a customized cell. We chose stainless steel as electrodes on either side, and we supply 2.5 milliamps current for 3 minutes for the polymer deposition on the stainless steel, and we change the polarity of the electrode and supply zero point 0.8 milliamps current for 30 seconds for the process of dedoping. Results. Dopant, doped P3MT is a P-type conducting polymer with band gap of 1.9 electron volt. These devices hardly show negative differential resistance. Dedoping is a process used to remove the dopant and form disorderliness on the surface of P3MT. Silver top contact is used to complete the device geometry, that is stainless steel, P3MT and AG. So the current voltage measurement is carried out on EF6 and ClO4 doped P3MT devices, which are dedoped for 30 seconds. Both the devices show negative differential resistance in negative bias region, and the slope of double logarithmic IV is found to be greater than 2, which attributes the charge transport mechanism in the device is due to trap assisted space charge limited current. It is observed that NDR in both the devices are affected by various parameters. NDR can be tuned by varying the dopant concentration, applied bias, and also by sweep direction. As mentioned, as we can observe in the first graph, uh, the black color IV represents the IV graph for EF6 dope device, and the red color represents for ClO4 device. And we can see that NDR is observed in both the devices in negative bias region, as mentioned earlier. So the inset of this graph shows the normalized current voltage graph. So as we can see, the NDR is more in ClO4 device than in PF6 device, and the peak voltage is higher, and the voltage swept for ClO4 device is higher, and the current ratio for from negative to positive is higher for ClO4 device. And all the results are mentioned in this tabular column. And this is a graph of uh, double logarithmic IV graph for PF6 dope, and this reveals that at lower applied bias it shows 2.44. The slope is 2.44, but at the higher end it is the slope is negative, which reveals that it is a NDR region. Similarly, in in CL4 device, we can see that the lower end is 3.74, which reveals that it is trap-induced space charge limited current, and the higher end it is negative differential resistance because the slope value is negative, and the inset of these two shows the positive bias fitting IV fitting for positive bias region, and that also shows SCLC or trap assisted SCLC in higher applied bias, but in lower applied bias, it shows Schottky emission, and that is due to that is because it has some voltage barrier. It has some barrier, and by applying some voltage, um the barrier decreases, and that is observed at lower applied bias. Thank you.